So now you will use the transition state theory expression to calculate the rate constant for the structureless molecules, and we should get the similar expression which we got in collision theory. Now, one important thing to note here is that we actually said this this frequency which is the characteristic frequency as nu dagger, but we don't need to calculate nu dagger because we set the K2 to be identical to nu dagger, and then one factor comes out when we do the calculate the particular partition function, the vibrational partition function for the for this transition state, and that also gives us a factor which is kBT by h into nu dagger, and this nu dagger now cancels out, which we have seen. So we don't need to actually focus much on to characterize which vibration giving rise to the product, or we don't need to actually identify the specific reaction coordinate, how the reaction is occurring. So we do not actually need to focus too much on the dynamics. Secondly, as you see here that there is no dynamics here, because we did not consider any dynamics here, that the molecules are colliding and they are forming on some activated complex and then it is reacting. It is very different from what we from our approach that we used for bimolecular reactions. So for a very complicated molecule like a big polyatomic molecule, when they are colliding and they are forming something for a bimolecular elementary reaction, we can right away apply the transition state theory if we know the from electronic structure theory the geometry of the activated complex, and if we can actually calculate the partition functions, which are again time independent quantity, because these are all equilibrium statistical thermodynamical properties, and we can calculate the partition functions, and then we are done. So all we are doing here is basically statistics, and the entire dynamics actually is gone, and that is the beauty of transition state theory, that although you are calculating a rate constant, which is a very much dynamical parameter, you are not doing any dynamical calculation explicitly, meaning you do not need to explicitly solve any dynamical equation like Newton's equation of motion or Schrodinger equation of motion. You are just simply doing statistical mechanics, and that too time independent statistical mechanics. Now let us do that. So for say if A and B are something like hard spheres, as we said, and the transition state will look like something like this, and where this distance, which is basically the center to center distance on the nuclear internuclear distance when these two spheres touch each other, that we denoted as Bmax in our derivation for the collision theory, which is nothing but the radius of A applies radius of B, and this will encounter soon. Now let us first try to calculate the partition functions. Now the expression for the rate constant is for the using the transition state theory is kBT by h, where kB is the Boltzmann constant, times we know that we have a partition function for AB dagger per unit volume, where we have taken out one vibrational degree of freedom divided by QA by V into QB by V into e to the power minus E star by kBT. Now we are going to only calculate this part, and then we can go back to this thing, because this part is similar to the collision theory, and this will see will be reduced to a useful version. So what will be the expression for this thing, which is QAB dagger by V with a prime. Now this is a diatomic molecule, and as you can realize that it has only one vibration, right? It's not a diatomic molecule, I should say it's basically bimolecular collision. These two are two molecules, and this is the AB thing, but again it's a crude thing in the sense that you can think that A and B are touching, and then of course in the transition state there is a vibration for the which is like AB vibration, but this is not exactly the AB vibration. So this is a oversimplified picture. This is some other vibration that will give me product, because if AB vibrates, it will be again A plus B, something like that. But we are talking about a reaction where it gives some product which we do not know. But we are just trying to mimic the collision theory approach to understand that this gives us the similar result. So I have AB, and here I have AB dagger. And now AB dagger, in the way we have drawn it, for 2 hard sphere, there will be only one vibration, and that one vibration already we have, let's assume that we have already calculated it. So in the AB dagger partition function, there will be only translation and rotation and electronic. So for translation, we know that what is the translation and partition function expression. So Q translation by V, we are actually associating the volume with the translation and partition function, and you know that it is basically 2 pi m kBt by h square raised to 3 by 2. Now 2 pi m, instead of m I have to now take Ma plus Mb, because that's the total mass of the activated complex. 2 pi m kBt divided by h bar squared raised to 3 by 2. Then it will have its vibration we have already taken care of, and it will have its own rotation, and the rotational partition function, if you remember the formula, it was 8 pi square I is the moment of inertia, kBt by h bar squared into sigma. Now sigma is the symmetry number, but it will be equal to 1 if A and B are different, and let us assume that A and B are different. If it is H and H, then you have to use actually a symmetry number of 2, because one rotation on half rotation gives you the same structure back. So we are not writing any symmetry factor here, and this is for a linear molecule, the rotational partition function. And the way you have drawn it, the transition state is also linear, because you have a sphere here, you have a sphere here, and then it's basically the rotation of that thing. So we are assuming it to be a sphere, and electronic partition function also, let us assume it to be 1. Let us not bother about the electronic partition function right now. Let us bother only about the, say, translational, rotation and vibrational partition function. Divided by, we had QA and QB. Now since these are hard sphere, they do not have any other degree of freedom, rather other than translational degree of freedom. So we have to consider only the translational partition function per unit volume for A as well as for B. So the way we are writing it, note carefully. So it is 2 pi m A kBt by h bar square. This is for QA by V, which we wrote here, and similarly for QB by V, we can also write similar expression, 2 pi m B kBt divided by h bar squared raised to the power 3 by 2, times we had kBt by h, and times we had e to the power minus E star by kBt. So what we get here, you can notice carefully that I have, let us first calculate the 3 by 2 terms. So I have kBt by h times, so as you can see, I have 2 pi here, kBt here, and h bar squared here. That will cancel with this. So these things will cancel with each other. Now what I am left with is 1 2 pi kBt by h bar squared, so in the denominator. So what I'll have here is 1 over, and then also notice that I'll have Ma times Mb, and in the numerator I have Ma plus Mb, so that I can actually write something like Ma Mb divided by Ma plus Mb, and then I have 1 2 pi Ma, all the combinations of Ma Mb, and I have also 1 kBt. So, and also I have one h bar squared, that raised to the power 3 by 2. So that is the 3 by 2 terms. Now you can see that this entire thing is nothing but my reduced mass of the system. So in the next line what I am going to do is that I will just replace it by the reduced mass mu. Now before we go there, I also have the rotational partition function, as you can see here. So that is 8 pi square, and then I. So what is I? I is moment of inertia. Now how do you define I? I is basically mu times the r square, but r is basically the radius of gyration, and then that is nothing but for this system is Bmax. So it is mu Bmax squared, and times I will have kBt and divided by h bar square, times I will have e to the power minus e star by kBt. Now we can arrange the terms one by one, and then you see here that I will have kBt. Let us write it once again, and times I will have h bar squared by 2 pi mu kBt raised to the power 3 by 2, and then I will have 8 pi square into moment of inertia is pi, sorry, it will be mu Bmax squared, not pi. It will be mu into Bmax squared into kBt divided by h bar squared into e to the power minus e star by kBt. We have to simplify this expression. So what I am going to do is that I know that I'll just, my purpose is to show it as the transition state expression. So I need 1 pi Bmax squared. So I can steal 1 pi from here, and the Bmax squared also I'm just keeping. So I'm just writing it as pi Bmax squared times, I'm also keeping this thing untouched, e to the power minus e star by kBt, and then let us see what we are left with. So we are left with 1 kBt by h here. Let us first calculate the kBts. So what we have kBt here, and then I have 1 kBt here. So this 2 gives me kBt squared, and then in the denominator I have kBt to the power 3 by 2. So it is kBt squared divided by kBt to the power 3 by 2. kBt squared is kBt to the power 4 by 2. So together I'll have kBt to the power half. And then what else? I have 1 mu here, and I have mu to the power 3 by 2 in the denominator. So I'll have mu to the power half in the denominator. And now let us calculate the h. So I'll have h here, and I have h bar squared here. Let us calculate the h bars first. So h bar squared and h bar squared here, they will it will be h bar squared and h bar squared. So I'll have h bar to the power half. But then also h bar is nothing but h by 2 pi. So in that sense I can write it as h by 2 pi, and then we can easily figure that out how it gets cancelled. So let us just do it. So this h is, I have 1 h here, as you can see, and then I'll have 1 h bar squared here, and I'll have h bar to the power 3 by 2, h bar squared to the power 3 by 2, so which is h bar cubed, and then I'll have 1 h bar squared instead of h bar. So let us write it once again. So I have this h bar squared and h bar cubed, so I have h bar divided by h, and that will give me basically 1 over 2 pi eventually, times what I have. Let us also calculate the 2 pi's. I have 2 pi here, and I have 8 pi here, because already 1 pi we took out for pi bmax square. So I have 8 pi divided by 2 pi to the power 3 by 2. 8 pi divided by 2 pi to the power 3 by 2, something like that. So that also we can simplify. So this is 2 pi and 2 pi to the power 3 by 2, it will be 2 pi to the power 5 by 2, and then this is a pi here. So you can easily simplify that thing, and ultimately what we will get is this 2 and 2 to the power 3 by 2, you will get the value of 8 kBT by pi. I have a mu here also, the entire thing raised to the power half, and then I have basically already derived the transition state the collision theory expression, and we see that the expressions are exactly the same. All right, now let us go back and look at the other expression for this collision theory, where we showed that not collision theory, transition state theory, where we showed that this entire thing, the expression can be written as kBT by h into some equilibrium constant. Now we can rewrite it as kTST is nothing but kBT by h into, I have some equilibrium constant for reactant to transition state equilibrium, but with the prime, and the prime denotes that the 1 degree of freedom is less. Now what we can do is that we can apply just classical thermodynamics, and we know that the relation for the equilibrium constant with the change in the free energy, and we are going to just use that relation. So we already know that del G is equal to minus RTL in K equilibrium. In this case it is for the transition state, so I am writing it as a del G dagger. So this is K equilibrium dagger with a prime sign, or we can just skip the prime sign, whichever it is. It denotes basically equilibrium between the reactant and the transition states. Now what is if we just write it, so we can easily get the expression as a to the power minus del G dagger by RT, and remembering that del G dagger has 1 degree of freedom less. Now what is del G? Del G is at constant pressure and temperature. It is del H minus T delta S. Of course it is at constant pressure and temperature, that's why we got this expression. Now what is del H? Del H is nothing but del of U plus PV if it is an ideal gas, assuming an ideal gas behavior and assuming a gas phase reaction. Now we have actually delta U. Delta U is a change in internal energy that is connected to the activation energy which RNA has got experimentally, because this is a macroscopic quantity which he measured. And E star or epsilon star, that notation is a microscopic quantity which actually denotes from the 0 point energy differences. And delta PV, now PV actually you can approximate further as ideal gas equation. So in the previous case when we write it H is U plus PV, that is not for ideal gas equation, that is by definition of enthalpy. And now we are applying the ideal gas equation, and where actually it is delta of nRT. Now RT is a constant, so it will be nothing but delta N times RT minus T into delta. So delta N here is basically the change in number of moles. Now for our reaction, if you think that I had a bimolecular reaction and that is forming a transition state which is just one molecule. So the change in number of moles is basically -1, because I had 2 moles here and 1 mole here. So it is 1 minus 2, which is -2. So you can right away write that it is nothing but delta EA. It will be a minus sign here. So minus RT minus T delta S. Now we can put it back into this equation. So what do you see here? It is kBT by H times e to the power minus, first I am writing this term, RT term. So e to the power minus RT by RT, minus RT by RT, it will be basically just E, or e to the power plus 1, times I'll have a factor which is e to the power minus EA by RT, and then I'll have a factor which is e to the power minus, not minus, it is a plus sign, delta S by R, because there was a T here, it cancels with this T here. So we can just rearrange the stuff, which is kBT by H into e to the power minus EA by RT, or we can actually keep all this form like kBT by H into E times e to the power delta S by R times e to the power minus EA by RT. Now you see that this has a similarity with the Arrhenius equation. Now the question is, what we get from this derivation is an expression for this A, which is the pre-exponential factor. Now what is the physical significance of the pre-exponential factor which we just derived from transition state theory? Now what you see here is a very interesting thing. It has a kBT by H factor, and then there is E is a constant, and it is a temperature dependent, of course, because there is a T here. Now it has this striking factor e to the power delta S by R. Now that is an entropic factor. Now think about it, if we have two body like A and B, a bimolecular reaction, and then it is forming the transition state, then the transition state is just one molecule. You can think of it. So in some sense, actually transition state is more ordered, because as you see that the change in entropy in this case is negative, which means the overall reaction probability will decrease once we go from the reactants to the transition state. That actually makes sense, because when you do make a derivation from the collision theory, you actually calculate all this, the A actually there is related to the number of collisions, because if you remember this collision cross section pi Bmax squared times the relative velocity, and these two things gives you basically the number of collision terms, and then there is an energy factor which is e to the power minus E by some energy by RT. But then you say that that energy factor takes care of the fact that all collisions does not give you the products. Only those collisions which can cross a certain amount of energy will give you the product. But then we always overestimate the reaction rate. The meaning of the overestimation is this, that your transition state has to be nicely oriented, in the sense like we always said that this A and B are kind of structureless in this case, but in reality A is a molecule, B is a molecule, and they have to actually collide in the right fashion. For example, suppose if you are talking about collision between two molecules, where these molecules are two functional groups which are like this, then these two functional groups should interact with each other like this. So if the collision happens like this, although energetically the collision may be favorable, orientationally it may not be favored. So this orientation factor is directly embedded in the entropic factor. So you have to have the right arrangement which will reduce the entropy of the system, because you are going from a less organized structure where the reactants are randomly moving around to a more organized structure in the transition state, for which the entropy should decrease, and then actually you can have a decrease in the reaction probability which you calculate, which actually takes care of all the orientational factor that you did not account for when you did a collision theory expression. This is how we can actually understand how the transition state theory can give me an interpretation of the pre-exponential factor in terms of the probability factor, which directly relates to an entropic factor. Now let us summarize this part. So what we did in this part is that we first started with a discussion on the potential energy surface. Now for a potential energy surface, we talked about always bimolecular reaction, and then we for developing the concept of the saddle point, we said we considered a reaction where actually an atom reacts with a diatom. It is also kind of a bimolecular reaction where one molecule is a diatom and the other molecule is just a monatomic molecule, something like that. And then we talked about a reaction like A plus BC, and we draw the potential energy surfaces, and we found that the reaction actually goes through a minimum energy path, minimum in the sense that whenever it moves, it actually moves along a minimum path which is minimum in the orthogonal direction, but then it actually goes through a maximum, and when it reaches its maxima, it means that it is, since it is always at the minima position in all other orthogonal direction, this point represents maxima on one direction and minima in all other direction. So it looks like a saddle, and that saddle point, you can think that the geometry of the saddle point is something like neither the AB bond is broken nor the BC bond is completely formed, and you call this thing as a transition state geometry, and this entire thing you call it as a complex, and you call it as an activated complex. Now then you formulate your theory and you say that this activated complex is in equilibrium with the reactants. So we can actually directly go from here. So A plus B is directly in equilibrium with some activated complex, and that gives rise to the products. And then you say that okay, fine, if it is in equilibrium, I can directly use the equilibrium approximation, and then you say that the rate of product formation be directly connected to the vibration of the activated complex, and the rest of the thing can be equated to an equilibrium constant which can be connected to the partition functions. And then you cleverly calculate the partition function where you separate 1 degree of freedom from the rest of the degrees of freedom, and that 1 degree of freedom we chose as a vibrational degree of freedom. You could also solve it as a translational degree of freedom. In that sense, actually you say that the entire molecule or the entire activated complex as if is moving across the transition state, and that translational degree of freedom you take into account, and you will get the similar answer. You will get the same Eyring equation kBT by H with multiplied by all this thing, but there actually you do 1 degree of less in the translational degree of freedom. We can actually give you a problem set where you will be asked to derive it in step by step, and then what you see here is that you can you get an AB dagger, and this AB dagger, the statistical properties of this AB dagger will control everything in the sense, if you can know the geometry of the molecule, you can actually calculate the partition functions, and then you can calculate the rate constant, and that is the entire essence of the transition state theory. And then we gave an example for structureless molecules like hard sphere molecules collision, and we showed that it right away reduces to the expression for the bimolecular collision theory. And then we said that for any transition state for a very complicated system, there you can think that there is a specific orientation for the transition state. So there is a geometry factor involved, and the geometry factor pushes the requirement that it is connected to an entropic factor. So the entropy actually is decreased because you are going from more random state to a more ordered state, and that accounts for the why actually you overestimate the reaction rate constant when you do it in a collision theory experiment, a collision theory way. So you can actually meet the correct energy requirement, but you may not be able to meet the correct orientation factor, because there is no way you can actually think about the orientation from a hard sphere model, because these are structureless, but you can incorporate into the transition state theory, and you can physically interpret it as an entropic factor. So in the next set of lectures, we'll see that how one can actually think about, so this is basically a transition state theory developed for bimolecular reaction, but similarly you could actually develop it for unimolecular reaction. But again, for unimolecular reaction, we discussed the Lindemann hypothesis, which talks about a bimolecular collision that precedes a unimolecular reaction, and then this energized molecule in the unimolecular reaction gives rise to the product. But we'll see if we can apply the similar transition state concept or the statistical concepts to understand or to get a derivation for or expression for the rate constant. Also, as a final note, as we discussed that the transition state exists at the saddle point, it is not always true because there are many sophisticated versions of this transition state theory, which basically talks about the trajectories for going from reactant to product. And then in the detailed quantum dynamical calculation shows that there could be some trajectories which actually come back on the near the transition state region. So you may, if you calculate at the number of trajectories at the saddle point, you may not get the correct answer because actually you might have a recrossing near the saddle point. So there actually you talk about a position of the transition state to be the position where the number of recrossings are minimum. So this is called a variational transition state theorem. I am not going into the details into that. Secondly, this transition state theory, when we derived it as a motion on the potential energy surface, and this is just one version of the transition state theory. There are also many other versions, and this version, as I said, that it is known as activated complex theory because we talk about a complex. But this complex, if you remember that this is not a stable complex because you have a barrier along the reaction coordinate. A complex means which is stable in all degrees of freedom, along all degrees of freedom, meaning reaction intermediate will be something like which has a minima even along the reaction coordinate. And so these are basically the transition state going from, say, a reactant to a bunch of reactant to bunch of products, and this is an intermediate. So in some sense, although we used the same concept that I have a reactant and which is in equilibrium with the intermediate, and we use the same pre-equilibrium concept for development of transition state theory. But there we have to be very careful. This is actually a transition state. This is not exactly an intermediate, and which is lying at the minima in all other direction, but at a maxima along the reaction coordinate. So it is not really a complex. So that's why this activated complex theory, this name complex, is a little bit misnomer. And thirdly, which is most important, this location of the transition state, the way we derived it is right at the saddle point, or you can think of it, it is at a particular point where actually the recrossings are of the trajectories are minimum. But the point here is that it has a very precise location. Now you could actually cast the entire problem instead of the, say, coordinate space energy versus coordinate space to a phase space problem where you represent the momentum and the position, and there also you represent the transition state as a point. If you have a point in the phase space, which means actually you are simultaneously specifying the momentum and the position with absolute precision, which means you are violating the uncertainty principle, which means actually transition state theory is inherently a classical theory. And this point was made by Wigner, and who did all this classical canonical partition function derivation, which also we did not derive. We just derived the Eyring model, which is not very rigorous model, but it is a correct model in the sense that ultimately at the end of the day, the Wigner's model with all this rigorous derivation also gives you the similar expression. And transition state theory had many drawbacks and many more discussion, as we just said, that the variational transition state theorem. There are also tunneling effects in the sense that when you go from reactant to products, you may actually tunnel through the barrier, and at low temperature this tunneling can contribute significantly to the reaction rate constant. But those details we are not going to discuss in this course. So we'll just stop our discussion on potential energy surface and transition state theory here. Thank you.